This video includes examples of working with non-unit circles. The first example is from the textbook on page 182, problem number 2. It gives us the point 5, 12 for the xy coordinate plane and asks us to find the trig functions of an angle, central angle, using that point on its terminal side. Let's go ahead and draw a picture of this. I'll plot just a set of xy axes, so we'll get a nice visual of this, x-axis horizontally, y-axis vertically, and then I want to plot the point 5, 12. So it goes 5 right and then 12 up, which would give us a point up here in quadrant 1 in that way. Now, if I draw a central angle in standard position that has that point on its terminal side, of course, standard position means one of the sides of this angle is along the x-axis, but then another side extends from the origin up through the point we've plotted at 5, 12. And I'm going to label that angle theta just to give it a name for now. Basically, we want to find the sine of theta, the cosine of theta, and the tangent of theta. That's our goal for this problem. Now recall, we know a lot about sine, cosine, and tangent, but most of what all of what we've memorized so far has been on the unit circle. This is not on a unit circle. In fact, I know that because the unit circle has a radius of 1. That would be the same as saying the distance from the origin to this point where I have here 5, 12 is 1, but we know it's not. In fact, I'm going to call it r for now. And I also am going to draw a triangle that's going to use these dimensions. So I'll draw a vertical side from our point straight down to the x-axis. And we already have the other value labeled here, 5, with a base along the x-axis. Now, to work with this triangle, I'm going to actually pull it out and redraw it, which is not necessary, but it just sometimes cleans it up a little bit to have separate pictures. So I'm going to have now just an abstracted triangle. I'm redrawing the same triangle. It has a right angle in the bottom right corner. It has an angle theta in the bottom left corner. And it has a vertical leg on the right side, horizontal leg on the bottom side. Now we know that from the way this point was given, the bottom side leg is of length 5. The vertical right side is of length 12. And the hypotenuse of this triangle across from the right angle, so far unlabeled, that would be labeled r in our diagram, which I have on the axes. But I'm not going to label it r yet here. In fact, we're going to find out exactly what that is. As you might recall, there's a way to find that. It's called the Pythagorean Theorem. The Pythagorean Theorem would tell us that x squared plus y squared equals r squared in this case, where the bottom side is x, the vertical side is y, and the hypotenuse is r. But we know two of those lengths. We know x is 5, so this means x squared is really 25. We know y is 12, so y squared is 144. And we can use this to solve for r. So this would give us that 169 equals r squared, which means r is plus or minus 13. We're just going to use the positive version for our radius, so 13 it is. I'm going to go ahead and label that on our separate triangle that's redrawn here, which means we now have 3 sides labeled, the bottom being 5, the vertical side being 12, and the hypotenuse being 13. The most important step is understanding which side of each of this triangle goes with which name label. If my angle theta is labeled where it is in this bottom left corner, I can look across from it at the side it's not touching and call that the opposite. Of course, there's always only one hypotenuse, and in this case that's across from the right angle, which is labeled 13. I'll label that hype for hypotenuse. And then the other side would be the adjacent side that's touching the angle. With those labels, I should be able to go ahead and define sine, cosine, and tangent according to the little acronym we recall. Sine is opposite over hypotenuse. Remember the SO acronym. Sine is opposite over hypotenuse. So if I go back to our triangle and just put those labels in place, opposite is 12, hypotenuse is 13. So the sine of angle theta is 12/13. Done. The cosine, of course, that acronym is CA, which stands for cosine is adjacent over hypotenuse. Those are labeled below. The adjacent is 5. The hypotenuse is 13. So 5 over 13 would be my cosine of theta. And of course then tangent, this is the TOA in the acronym. Tangent is opposite over adjacent, so opposite is labeled as 12, and adjacent is labeled as 5. And there we have it. As you can tell, the biggest part of this problem is labeling the triangle correctly with the right opposite, adjacent, and hypotenuse labels. Once you get those, and if you know the SOHCAHTOA acronym, getting these ratios for the values of sine, cosine, and tangent of theta is really no problem at all. Let's take a look at another example, this time on the same page, but problem number 4. And in this problem, they still want us to do the same thing, which is find sine, cosine, and tangent of theta, where theta is in standard position, a central angle that has the point, this time, -1, 5 on its terminal side. Let's go ahead and draw, again, a diagram that will help hold all this information for us. I'll draw a vertical y-axis, a horizontal x-axis, and we want to label that point or plot that point on it. -1, 5 would occur way up here in quadrant 2, 1 left, 5 up. And so from that label, I want to draw or connect from that point a radius, which extends all the way to the origin of the axes. And then I want to draw a triangle out of this. So I'll extend a side straight down from the point to the x-axis, and we already have the bottom side drawn really as part of the x-axis there. If this point truly is -1, 5, then we can label the sides accordingly. The vertical side of this triangle should be 5 units up. The horizontal side of this triangle is 1 unit left. Now, left and right have directions that matter in the coordinate plane, and though the distance from the origin to the right angle of this triangle in the bottom left corner is just 1, and normally you just label it 1 as a distance, I'm actually going to label it -1 for reasons you'll see in a moment. So since the coordinate is -1 and that meant going left 1, I'm actually going to label the side as -1. Now, as we did before, I think it's helpful to redraw the triangle separately just to get a cleaner look at it. So I'm going to draw a right triangle that's oriented in the same way as our triangle was on the axes, the right angle being in the bottom left corner. And then I'm going to put angle theta in the central angle position, which would occur at the origin. It's kind of tight up in the coordinate graph label, but I'm going to sneak it in there too. So theta is in the bottom right corner, right at the central angle position. And then let's label our sides accordingly. This vertical side is 5, the bottom is -1, and of course the hypotenuse across from the right angle is r. Now remember, we can find r by using the Pythagorean Theorem. That would state that 5 squared plus -1 squared equals r squared, which means 25 plus 1 is r squared. Notice squaring a negative makes it positive. That works out conveniently. So this means r squared is 26, which means r is plus or minus the square root of 26. We'll only use the positive version for a distance here as the radius. So positive root 26. Now recall, my whole point of doing this is I want to find what the cosine of theta is, the sine of theta, and the tangent of theta. And as we start to remember or memorize the acronym SOHCAHTOA, we'll recall that those are just simple ratios as long as I know the side lengths of this triangle and the central angle. Now, one issue with this example that we did not see last time is that this angle theta, the way I have it drawn, remember this triangle ended up in quadrant 2. So really this angle theta is not a standard position angle. Why? Well, because one of its sides extends across the negative x-axis from the origin, not the positive. In other words, the angle theta that would be correctly drawn as a standard position central angle would actually extend from the positive x-axis all the way up to this radius going counterclockwise. So this is the real theta, but the way I have it labeled in the triangle is that theta is over here on the other side of our terminal side of the angle. And as long as we label these sides with appropriate negatives, meaning, remember I labeled the bottom side of this triangle -1? Yeah, that matters because the fact that I labeled it negative will take care of the fact that we've also shifted theta and put it over here inside the triangle on the, quote, wrong side. All right, let's see how this all works out with our ratios. Cosine is adjacent over hypotenuse. So let's go back to our redrawn triangle at the bottom now, and maybe it might help still to label our sides. Across from our angle theta, of course, we have the opposite side. That's where 5 is labeled. On the bottom side, where we have -1 labeled, that's going to be our adjacent. And then, of course, the hypotenuse is always the hypotenuse across from the right angle. That's where the square root of 26 is labeled. So using those labels, let's go ahead and fill in our ratios. Cosine is adjacent over hypotenuse. Now that's going to be labeled as -1 over the square root of 26. And again, the fact that I've called this side -1, which is from the direction we went in the triangle on the axes originally, that will account for the fact that really I've mislabeled theta on purpose. I've put theta in the triangle, which is now in quadrant 2, but really theta should be the central angle labeled in standard position as it is in quotes in our original diagram up here on the top left. So the negative sign will take care of all that, which means I'm going to rewrite this as -1 over the square root of 26. All right, sine is opposite over hypotenuse. Well, given the way we've labeled this, that should be 5 over the square root of 26. And that, though you could rationalize, you don't have to. If you did rationalize, that'd also be the same as 5 root 26 over 26. It's good to practice both ways, I guess, but they're both equivalent. And then tangent, of course, being opposite over adjacent, would be labeled as 5 over -1. So again, we'll call that -5, and the fact that it's negative matters. That's going to account for the fact that theta really would be extending all the way from the positive x-axis to quadrant 2, where our terminal side of our angle exists. But we've redrawn theta to be inside our triangle here on the other side of that terminal side of the angle. And then one way to double check to make sure that you've labeled theta correctly is just to do a quick quadrant check on the signs of these. Recall, tangent, actually sine, cosine, and tangent all have different positive or negative values depending on which quadrant you're in. So quadrant 1, quadrant 2, quadrant 3, and quadrant 4 should tell you something about the signs of sine, cosine, and tangent, and those should match up. Notice our cosine value ended up negative as -1 over root 26. Again, you could rationalize that cosine value also and make it negative root 26 over 26. That's fine, either way. The sine value of our theta is 5 root 26 over 26, or 5 over root 26. Notice that it ended up positive, and this is making sense because theta should extend all the way to quadrant 2, and in that quadrant, cosine would be negative and sine would be positive. And then thirdly, tangent ended up negative as -5, but again, as you might recall, tangent is negative in quadrant 2 as well. So those are all lining up. Let's look at another example, this one on page 183, number 20 from the textbook. And in this example, they give us a couple pieces of information, namely that the cotangent of angle beta, this is the Greek letter B for beta, so cotangent of beta is equal to -2, and they tell us the cosine of beta is greater than 0 or positive. Now let's see if we can recall what that tells us. And by the way, they want us to find all the other trig values for angle beta. So we'll end up finding sine, tangent, cotangent, secant, cosecant, all the values that we know, all the function values we know for angle beta. Now if cotangent of beta is given as -2, notice it's negative. The fact that a cotangent value is negative, if you recall the cotangent different signs in different quadrants, this means it would have to be either quadrant 2 or quadrant 4. But we're not totally sure which one yet, so let's move on. The fact that cosine of beta is positive, that actually limits which option it could be, right? Because cosine is positive in quadrants 1 or 4. And so if these two stipulations go together, the only way they overlap is both true would be in quadrant 4. So this will tell us exactly where and how to draw our angle. Let's go ahead and sketch it now. I'll throw some axes out here, an x and y axis. And we know our angle is in quadrant 4, so I'm going to draw a terminal side of an angle that extends from the origin out to some point in quadrant 4. And we know that if this is in standard position, one side of the angle would extend across the positive x-axis, and the other side would be this side I have drawn from the origin out to a point here in quadrant 4. Now I'll extend a vertical side length to make a right triangle out of this angle. The right triangle now being in the upper right corner. That vertical distance we'll call y. The horizontal distance across the top of the triangle, which is the x-axis, I'll call x. And then of course the hypotenuse we'll call r for now. And they tell us some information about this, but until we get our triangle drawn and labeled, we can't do a whole lot with this given information. So I'm going to redraw the triangle in the same orientation. So right angle in the top right corner, hypotenuse on the bottom left side, I'll label that r, and then our vertical side length I'll call y, and our horizontal side length on top I'll call x. But notice we don't really have any numbers on these diagrams yet. So now let's go back to the given information, and the only one of them actually had a number with it. That was that cotangent of beta is -2. Now I should label beta on here. Remember, this is in standard position. I'll label beta on the axis drawing, or the axes drawing, as the angle in the top left corner right at the origin in standard position. And then I'm going to relabel it also in my redrawn triangle I have here at the bottom. So beta would be in the top left corner of this triangle. Now, all we know is that the cotangent of beta is -2. Let's see if we can get some more info out of this. If the cotangent of beta is what I have to work with, remember, cotangent is really 1 over tangent of beta. And the tangent of beta, as you might recall, tangent is opposite over adjacent. So let's go ahead and label our sides. The beta angle is labeled across from it, which I have currently labeled y. That would be our opposite side. The hypotenuse, of course, is labeled as r, the radius. And then the adjacent side for this one is where the x is labeled. It's touching the beta angle. Right next to it, the other side we have. So 3 sides labeled here accordingly. Cotangent is 1 over tangent, which would be 1 over opposite over adjacent. And we can say that's really equal to 1 over the opposite is where the y is labeled, and the adjacent is where the x is labeled. In other words, 1 over y over x is really just x over y if you flip over the fraction with the reciprocal. All right, so in other words, we know that cotangent of beta is really equal to x over y. But they told us that cotangent of beta is equal to -2. Now, first of all, 2 things. The negative sign makes sense because cotangent in quadrant 4, which is where we are, is negative. So that's good to know. And furthermore, I can set this number, -2, for cotangent as a fraction, which is -2 over 1. And if I know that the cotangent should be the ratio x over y, as we computed a minute ago, then I know that I can set -2 over 1 as x over y, which means x would be -2 or +2, and then y would be 1 or -1. Let's talk about the different possibilities of those different signs on there. If my terminal side of the angle is in quadrant 4, then imagine the x-coordinate would have to be positive, which means I'm going to let this negative sign go with the 1 down below. So I'm going to say x is +2. The y value of this angle, the y value of this point would have to be negative since it extends down below the x-axis. So I can say for sure that the y value would have to be the -1, so that the signs of all our values work here. If that's the case, let's go back to our triangle and label those. The x value is 2, the y value is -1, and the radius, or the hypotenuse in this case, we can find, again, using the Pythagorean Theorem. So let's crunch those numbers here quickly. We know that 2 squared plus -1 squared equals r squared. This means r squared equals 5, which means r equals the square root of 5. Okay, so the hypotenuse, which is the labeled r for radius, we know now is the square root of 5. Again, we use the positive value for radius every time. And since we have those labels now, or those lengths, we can get all the other trig functions we need. Let's go ahead and compute those now. So the sine of beta is opposite over hypotenuse. Well, for us, that would be -1 over root 5. Okay, that could be rationalized, but we don't have to. The cosine of beta would be adjacent over hypotenuse. Adjacent is labeled as 2. The hypotenuse is root 5. The tangent, of course, that's 1 over cotangent, which we already have above. So we'll say the tangent of beta would be -1/2. And a couple more to go. The secant of beta, secant is 1 over cosine, so we just flip cosine over to get root 5 over 2. And then the cosecant of beta would be 1 over sine, so that'd be 1 over -1 over root 5, or in other words, negative root 5 over 1. That's just the reciprocal of sine, or just negative root 5, you could call that. Okay, and there we have it. So from just this given information where we started, we were able to generate the diagram, label it accordingly, and therefore use all our trig ratios and understandings for these functions to generate the values for the sine, cosine, tangent, secant, and cosecant of beta. The next example I want to look at is on page 183, number 28, and it asks us to find the value for the sine squared of 660 degrees. Now, as you'll recall, 660 degrees is not within one wrap of the circle. By now, we've also been working with degrees a little bit, so we can hopefully understand the unit circle in terms of radians or degrees. Let me just do a quick sketch to remind us of the unit circle and the fact that one distance all the way around would be 360 degrees. So this is certainly much more than that. Now, it's not quite 2 full circles, because that would be 720, so we're a little bit short of that. Now, instead of actually drawing a spiral to measure where exactly this is, which could work, let's use what we understand about the periodic nature of trig functions. What is the period of sine, the basic period of sine? That's right, it's either 2 pi, or you could just say also 360 degrees, the same thing. Which means I can add or subtract 360 degrees as many times as I want for this input degree measure, and the sine value I get will not change at all. That's what a period is for. So the way we're going to handle this is we're going to take our given input angle of 660 degrees and start, in this case I want to subtract to make it smaller. I want to subtract the period value of 360 as many times as I need to get it within one circle wrap, just so it's much easier to identify where it'd be on the unit circle. So let's take 660 and subtract 360 one time, see where that takes us. Of course, that'll give us 300 degrees. And as you might recall, that's much easier to place on the unit circle and therefore find the sine value of it. So let's go ahead and find where 300 would be. On the unit circle, it'd be 60 degrees here below going clockwise. And that's one of our special places. So we can hopefully recall what the sine values are there. Remember, this would be, if there are 3 tick marks, this would be the third one of those near the bottom of quadrant 4. The sine value there would be the y-coordinate of that point. Okay, the x-coordinate there would be 1/2. The y-coordinate would be negative root 3 over 2. And so since the sine value is just the y value here, we can use, by the way, we can use the unit circle because no other measurements have been given for the side length of any kind of angle or triangle. So when in doubt, you can put things on the unit circle here, especially for degrees and angles. All right, so we know that the sine of 300 degrees is negative root 3 over 2. Where this problem started was with us trying to find out what the sine squared of 660 degrees is. So let's kind of just draw this out a little bit. First of all, the fact that it's sine squared means another way to write that conveniently is that it's the same as the sine of 660 degrees, whatever that value is, squared. Remember, that exponent can be thrown all the way on the outside, which means I want to figure out what the sine of 660 is. But since that's the same thing as the sine of 300 plus 360. And since 360 is the period of sine, and adding a period changes nothing for the output of this function, that's the whole point of a periodic function, then I can say that this is the same as the sine of 300, which we computed above as negative root 3 over 2 squared. So I'll square those values to end up with a positive value of 3 over 4. Our next example is from page 184, problem number 54. And in this example, they tell us that alpha, yes, that's what this letter is called, a Greek letter A. So alpha, kind of looks like a little bit of a fish or something. Alpha equals the cosine inverse of root 2 over 2. And of course, they want us to find the exact value of alpha. We're going to apply the cosine function to each side. I'm motivated to use cosine because I'm given a cosine inverse here. So if I take the cosine of each side of this equation, I'll end up having the cosine of alpha equals the cosine of the right side of this, which is the cosine inverse of square root of 2 over 2. Okay, and this will get me a lot further because I can use, on the left side, I just have the cosine of alpha. On the right side, I have a cosine of a cosine inverse. Well, those, by their very nature, cancel out, so I'm left with just root 2 over 2. Now, we have to figure out where this is on the circle in order to get further on what alpha should be. And I believe this problem asks for the answer in degrees. We can do degrees or radians, doesn't matter. I'm going to draw a blank unit circle in the bottom left corner here. So just a blank circle on the axes. And let's recall that we actually have a choice of where alpha could be, because cosine having a positive value of root 2 over 2 occurs at two places, either halfway through quadrant 1 or halfway through quadrant 4. You'll recall the symmetry would indicate that those two values have the same x value, and that's exactly where root 2 over 2 would be. So remember, those tick marks are halfway in between. So then, which one is it? Is it the angle that extends through quadrant 1 or the one that extends through quadrant 4? Well, this is where we need to recall the range of the cosine inverse function. That's right, all those intervals matter. So if you might recall, the range for cosine inverse, which typically the book just uses the letter y and puts some boundaries on it, the range, or in other words, cosine inverse values can occur between and including 0 and pi. All right, so this range among the others for the other functions is something we definitely need to know, because this will tell us exactly which of these two options we have to pick. If cosine inverse values have to have this bound between 0 and pi, that means our answer has to be somewhere in the top half of the unit circle. Well, that eliminates one of our options down here in quadrant 4, so we're going to have to use this option in quadrant 1, which means our angle, alpha, could be, well, the radian equivalent there, of course, would be pi over 4. I think they asked for degrees on this one, so that would be the same thing as 45 degrees. Be aware, in these types of problems, you're often given two options. If you just look at the raw unit circle, you have to decide between which option is correct based on the range of the given inverse function, as we just did here. Our next example is from page 185, number 66, and we're asked to find the exact value of this expression here, the cosecant of the cotangent inverse of 4/3. So exact value means we want a non-decimal answer, which means no calculator for this one. We want the exact unit circle value of some kind. A convenient way to organize these is to take the inner part of this function, which in this case is the cotangent inverse of 4/3, and give that a new name. I'm just going to call that theta for now. So in fact, let me write out that theta, I'll do this over here on the side now, so theta equals the cotangent inverse of 4/3. Okay, that's what I've just designed theta to be here. If that's the case, then again, algebraically, I could just apply the cotangent function to both sides of this equation, which would result in the cotangent of theta equal to the cotangent of the cotangent inverse of 4/3. But the whole point of this is that the cotangent of the cotangent inverse, those cancel. which means we're left with the cotangent of theta equal to 4/3. Now, that's not immediately obvious because, first of all, you probably or may not have all the cotangent values, even of the unit circle, memorized. And even if you did, you wouldn't find 4/3 as one of those values. So we're going to have to use some of the non-unit circle things we've learned earlier to handle this example. Let's recall that cotangent is really 1 over tangent. So if the cotangent of theta is 4/3, that of course means that the tangent of theta is 3/4. Let's get a little sketch of the axes going here so we can start to understand where things are occurring. Tangent is given here now as positive 3/4. Well, tangent is only positive in two quadrants, either quadrant 1 or quadrant 3. So we know that our angle, in this case theta, has to extend to one of those two quadrants. Which one of those it is will depend, again, here we go, on the range of cotangent inverse. So if I use the letter y to discuss the range, you'll recall that the range for cotangent inverse is that y has to be strictly between 0 and pi. So once again, yes, those need to be memorized, all the ranges of all the inverse functions. And in this case, that will tell you exactly which of these two quadrants we need to use. 0 and pi, of course, is this top half of the circle. That's where I'm allowed to be, which means I really want to use quadrant 1. I can't use quadrant 3 here. All right, in that case, all I need to do is draw a central angle in that quadrant. It's a right triangle that I'll make out of that central angle going down to the x-axis. And I'm going to label the sides accordingly, right? So theta will be the standard position central angle here near the axis in the inside of the triangle. And if tangent is equal to opposite over adjacent, then that tells me the opposite is 3 and the adjacent is 4. So I can label those accordingly. Opposite of this angle would be the vertical side here as 3. Adjacent would be the x-axis side as 4. And then I could use the Pythagorean theorem to find the radius of this. So 3 squared plus 4 squared would be r squared. That would tell me that r should be 5. All right, so that's just using the Pythagorean theorem. I didn't write out a couple of those steps there, but that's all that is. The radius is 5. So now, what does that help with? Well, if you go way back to the beginning where we started, our goal is to find the cosecant of the cotangent inverse of 4/3. We kind of divided this problem up and have spent all our time working on the inner part here, the cotangent inverse of 4/3. We called that theta, and then we did a whole bunch of work to figure out where theta would turn out on the axes drawn here, which is a non-unit circle, but we drew a triangle for it. And if we have that theta angle labeled as part of a triangle, then we can use the ratios we understand. Sometimes it's helpful to redraw the triangle. I'll do that here, though not necessary. I'm just going to take the triangle we have, redraw it, and label the sides. Theta is in the bottom left corner, which means this side is opposite. This side at the bottom is adjacent, and the hypotenuse, of course, is always a radius there. Cosecant of theta is what we're actually looking for. That's what the original one said there, right? Cosecant of theta was our input. So the cosecant is really 1 over sine of theta. Well, sine of theta we can now use as our trig ratios with the triangle. Sine is opposite over hypotenuse. The way those are labeled in our diagram is 3 over 5. So 1 over the sine of theta, sine is opposite, which is 3, over hypotenuse, which is 5. So 1 over 3/5 is the same thing as 5/3, which means there we have it. The cosecant of our angle theta is 5/3. And of course, we designated angle theta to be this inner part of the original problem. So 5/3 is our final result.